Now let's look at the age of the Earth. How we measure it, how we know what the history of life is, so we can piece together with absolute dates rather than just relative ages. Here's the full span of life on Earth, marking out the first traces of life, the first fossil bacteria about 3.5 billion years ago, the first cells with nuclei about 2 billion years ago, and then in a concentrated form expanded in the upper part of the diagram, the Cambrian and Precambrian eras, when the large creatures of the Earth developed. Early thoughts on the history of the Earth, of course, are all over the map. From Persia, 3,600 years ago, we have Zoroaster, the idea that the Earth is about 12,000 years old. We have, however, almost in the same time frame, ancient Hindu scripts that speculate that the age of the Earth and the universe is billions of years old. So ancient cultures in a pre-scientific era were still wrestling with the possibility of huge spans of time. A Neo-Babylonian empire, the Chaldeans, speculated that the Earth was about 2 million years old, about 1,500 years ago. In the more recent past, due to Christian theology, we have quite specific ages of the Earth for somewhere between 55 and 9,000 years old, and the timing of a biblical flood. On the right, we see an example of this estimate using the counting the begats, or generations from the Bible method of John Lightfoot from 1647. But then we go to observations of the natural world, and the estimates get a little better, or at least based on science. Benoit de Maillet in France speculated the Earth was 2.5 million years old based on an extrapolation of the level of erosion of the sea level in a place familiar to him. The Comte de Buffon, also in France, a little later in the 18th century, estimated the age of the Earth at 75,000 years, based on an interesting method. He watched iron spheres cooling of different masses and sizes, and then extrapolated them to the size of the Earth, imagining that the Earth had formed and was hot and had cooled over time. He got the time wrong, but the method was not a bad idea, and some version of that actually works better if you do it more accurately. From the mid to the late 1800s, the age of the Earth became one of the most hotly debated subjects in the science. Physicists had their own ways of estimating it, but biologists were increasingly aware that enormous spans of time were needed for natural selection to operate, and so there was a very active debate over the age of the Earth. The physicists were tending to give low numbers, perhaps tens or hundreds of millions of years. And this debate was because the biologists had used the accumulation rate of sediments in the fossil record to estimate that the Earth must have to be several billion years old for natural selection to operate. This crisis point came when Lord Kelvin published the first of his heat flow calculations for the cooling of the Earth and came up with an estimate of under 500 million years. Kelvin was the preeminent physicist of the second half of the 19th century, and Darwin was well aware that this estimate was probably insufficient for his mechanism of natural selection to work. The geologists and biologists were closer to being correct. It wasn't until the discovery of radioactivity by physicists that they were able to do absolute age for the first time. So we can look at that. From the late 1800s to the early 1900s, Rutherford and Soddy published The Cause and Nature of Radioactivity. Natural decay of heavy nuclei supplies internal heat, and it's that extra heat source that invalidated Kelvin's cooling calculations, and that's what led him to predict that the Earth cools too quickly, because the Earth has its own internal heat source from heavy or radioactive elements. That same radioactive decay provides the basis for modern isotopic dating. It wasn't a precision science until the 1940s and 50s, however. Here's how it works. Radiometric decay has an unstable radioactive isotope, a heavy element, and then a daughter product, which are the isotopes resulting from the decay of the parent. In the decay process, energy is released, and sometimes particles, electrons or alpha particles, which are helium nuclei. The half-life is defined as the time for 1/2 of the radioactive nuclei in any sample to spontaneously decay. The principle of radioactive dating is that the percentage of radioactive atoms that decay during one half-life is always the same. It's a statistical method, however. The actual number of atoms that decay will continuously decrease. So after one half-life, half of the original atoms are left because half have decayed. After another half-life, half of those remaining have decayed, and you're down to a quarter of the original atoms. By comparing the ratio of the parent to daughter atoms in the sample, you get the age of the sample. Radiometric methods do have some sources of error. We have to assume a closed system, and to avoid potential problems, only fresh or unweathered rock samples should be used. For short spans, including living organisms, a short radioactive half-life is used, and that's typically radioactive carbon-14. That's the isotope of normal carbon, which when a living creature dies, stops being metabolized and incorporated into the creature and starts to decay. With a half-life of 5,700 years, carbon-14 is useful for measuring the age of things in the range of 5 to 50,000 years. So it's only useful for dating recent events or biological organisms. Carbon-14 is produced in the upper atmosphere. For primordial Earth and the age of the Earth, we tend to use longer half-lives, and so the half-lives seen on the right here of 1 billion years, and especially uranium-235 with a half-life of 700 million years, are the most useful for measuring absolute geological time. How do we know that isotopic dating actually works? Well, we can actually compare ages from two different methods, and we know the age and we calculate the age for carbon-14. We can see that living creatures line up pretty well, and so carbon-14 is an excellent tracer, and it's well calibrated back to 20 or 30,000 years. We can also define geological boundaries because there are places where fossils appear and disappear, and then we can age date the rock itself and find the ages of the geological boundaries and map them out to the fossils. From all this work, what is the age of the Earth? The oldest rocks from many continents are in the range of 3.5 to 4 billion years. The oldest intact rock is a volcanic gneiss from the Greenland region, which is 4 billion years old. There are individual zircon crystals from Western Australia that are 4.4 billion years old. That's the oldest material that's ever been found on the Earth. Meteorites have been dated by numerous methods. They are primordial solar system material that are in the range of 4.53 to 4.58 billion years. And that essentially sets the boundary for the age of the Earth and the solar system. We've dated the moon rocks also to be 4.4 to 4.5 billion years. If you put all this together, you get a consistency age of around 4.54 billion years. It's the currently accepted age, and the error in this number is in the second decimal place, is about 1 or 2%. This age is comfortably consistent with astrophysics, the estimate of the age of our galaxy of 11 to 13 billion years, and the 13.8 billion year age of the universe. So the Earth formed about 2/3 the way the history of the universe to this point. Here's a picture of the Earth's oldest rock, a zircon crystal that was found in the Jack Hills region of Western Australia. This tiny crystal is durable because of its location and because this is ancient shield rock in Western Australia, so its chemical stability has not been altered over a long period of time. Remarkably, chemical analysis of these crystals allow us to infer that the Earth had a temperate climate and had stable bodies of liquid water 4.4 billion years ago. Remember, that's just 100 million years after the Earth formed. And so it is conceivable, it's possible, that life started on the Earth very early in the history. And that's the end of this topic.